Topic 1, CBUS method. Today, we are going to start from chapter 1, which is focusing a CBUS method focused on trust analysis, trust structures. You have some idea right now about what is so-called CBUS method, which is a matrix method. Trust means actually loaded member. How to analyze trust structures using CBUS method. This is the target of this chapter, of this topic. This is the outline of this particular chapter. At the beginning, I will briefly introduce the overall background of CBUS method. And then, starting from the second sections, we focus on trust element, how to formulate the equation for trust element, trust member. And then we need to play with something so-called transformations. You will learn very soon why we need to transform matrix. And then formulate the global equations, the trust structures, CBUS matrix. The first 5 sections basically about formulation, derivations. And then starting from section 6, here we start to discuss how to apply CBUS method to analyze trust structures, applications. Chapter 7, we discuss the other external effects. Other than external loading, structures may sometimes under the other actions like the thermal change. Thermal change means temperature change. Under temperature change, internal force will develop inside the structures. Under high temperature, we may have internal stresses. We will start to discuss how to handle thermal change right here. And fabrication error, sometimes the member may be too long or too short due to fabrication errors. When you fit them inside the structures, it may also induce initial forces inside the structures. We will discuss how to play with these 2 external effects using CBUS method. Finally, space trust. Space means 3D trust. But you can see a star right here, which means that it is a reference. Oh, I put down the meaning here, reference. The star means reference. I give you some idea to see how you can extend the contents from 2D to 3D. In this module, we basically focus on 2D structures. Most of the times, we are talking about 2D. For 3D, we will introduce the idea, but not for assessment, because the calculation is too heavy for 3D. At the beginning, let us talk about the fundamental issue of CBUS method. CBUS method is classified under the category displacement method. It's a displacement method of analysis. We firstly find out displacement and then use the results to find out the unknown reaction or internal forces. Displacement method. Okay, displacement method, we firstly find out displacement and then followed by the forces. CBUS method is quite general. It's derived mainly based on equilibrium, based on principle of superpositions. Principle of superpositions is a very important principle in engineering practice. Many theories are derived based on principle of superpositions. If you want to use this principle, remember that the material should be linear elastic. Otherwise, you can't apply this principle. And this method is intended to solve indeterminate structures, but actually it can also be used to analyze determinate structures. So that's why CBUS method is very general. It can handle both determinant and indeterminate structures. But we seldom use it to handle determinant structures, because for determinant structures, you have some more easy way to find out the response. Normally, we don't want to use this complex matrix method to handle simple things. But for indeterminate structures, you may use this method, quite efficient and general. You can handle all the things. In the past, when you learn CBUS method, when you learn slope diffraction method, moment distribution method, etc., they are basically for some specific problems. But for CBUS method, to all. You can use the same approach to play with all kinds of structures. X can give you displacement and forces directly. Two important responses. These are the two things we want to know, right? Displacement. When you design a beam, you have to check RC beam, for example. You have to check the span depth ratio, right? When you design a steel beam, you have to check the diffraction directly. How to find out diffractions? You may use this approach. Force. When you want to design a beam, no matter steel beam or RC beam, you need to know the internal forces, shear force, moment, axial force, etc. You can also use this approach to find out the response directly. And this is a matrix method. We convert a structural problems to a matrix equation. By solving the matrix equation, you get all the things, displacement and forces. At this moment, you have no idea why we use matrix, but after talking about the second chapter, I mean the next part, then you will know why we can convert the problems to matrix. This approach is extremely suitable for computer operations. Computer can handle matrix calculation efficiently, right? Say, for example, if you use Excel can also help you to solve this matrix problem. I will let you know how to solve a problem using Excel later. So the key concept of this method is to subdivide the whole structures into a series of discrete Further elements, and each of them has a unique nodes. This is the key things of this method, simplest method. Subdivide the whole structure into different discrete elements. Just reading this statement is quite confusing. I give you one picture to let you know what is the meaning. Given the structures right here, we have a truss structures composed of three elements, three truss elements. You can decompose, you can say that these structures composed of three truss elements. And each element has two nodes. Say, for example, we have three elements, element 1, element 2, element 3. And these nodes are normally used a square and then covered by numbers, used to denote the element numbers. We have element 1, element 2, and element 3. They are the element symbol. You can arrange the element symbol in arbitrary manner. The purpose is just used to help us to for communication purpose. If I say element 1, then you can see the location clearly, right? They are used to communicate. So in theory, you can arrange the element number in arbitrary manner. If you like, you may call this element 1, element 2, element 3. No difference, okay, no difference, same. We use square to denote the element number. We have three elements, 1, 2, 3. Each element has two nodes. For element 1, we have two nodes, one at the top, one at the bottom. Element 2, similarly. Some nodes are overlapping to each other. Say, for example, this node. You can see that element 1, 2, 3 all connected to the same nodes, common nodes. In this module, we use a circle. We use a circle to denote the node number. Similarly, node number help us to describe the positions. Node 1 is the bottom right-hand corner. Node 2, top right-hand corner, and so on. You can arrange the node number in arbitrary manner as well. They are just for communications. The exact order is not very important. No matter how you arrange the number, you can get the same result if you do all the calculation in the correct manner. As mentioned that we can decompose our whole structures into different tiny elements. Here, I isolated element 3 out. Element 3 is a truss member with two nodes. Truss mean what? Truss means it is an actually loaded member. Actually loaded member means it has axial force only, right? No bending moment, no shear force. Truss element only under axial force. It can be in tension, it can be in compressions. Although I put down compression here, but you know it can be in tension, right? The direction of the arrow just for illustration only. We have axial force. Similarly, we have displacement. The member may under elongation or shortening. So you can see that this is the expression for one element, truss. You can use the same picture for element 2, for element 3, but they have different orientations. For each element, you can set up a local force displacement relationships. I will let you know how to do it very soon. For each element 1, element 2, element 3, you can set up a force displacement relationship for each element. And then, say for example, this is the equation for element 3. I is just used to denote the element number 1, 2, 3, or maybe 4, and so on, if you have a big scale structures. Q is force, actual force. D, displacement. So what is this called? Hooke's law, right? F equal to K times D. In your physics module, maybe we have an equation for a spring. Force equal to a spring constant times displacement. Actually, same things. I just changed the symbol a little bit. And then they are not scalar. They can be a vector or a matrix. This is the equation for one element, right? But we have 3 elements here. You can use this equation 3 times for element 1, element 2, element 3, and then combine them together to represent the whole structures. You can add up the 3 equations together, becomes a whole structural problems. I use capital Q to denote the property along the whole structures, not single element, but the whole structures. Capital K is the structure sequence matrix for the whole structures. I will let you know how to set up the matrix and then how to solve it later. But you can see that firstly, we derive the individual equation and then put them together, becomes a big matrix equations. Solve it, then you can get all the response, displacement and member forces. These are the general procedure of Sibyl's method. This is true for truss, for beam, for frame. Okay, this concept is true for truss, beam, and frame. Similar concept. So in our following sections, we will firstly discuss how to set up local equation for each member. Okay, and then we will discuss how to put them together. Finally, solve it. I think the new part is here. Point 1 and point 2, they're new. How to set up the equation in member level and then put them together. Point 3 is not new. It's just solving a matrix problem. You have to learn how to play with matrix equation in matrix algebra. Some fundamental math modules. More about discretizations. This is the key things of using Sibyl's method. For truss structures, as spoken before, you can decompose a truss structures to n truss element. Say, for example, for these truss structures, you can see that it's composed of 6 members. Right? So basically, you can decompose this into 6 members with 4 common nodes. 6 members. You can imagine that if you have the second story, then you can do the same approach, right? Discretize the second story into n element as well. This is called discretizations. This idea can be applied also for truss bridge. Discretize the structures into n elements. One remark is that here we treat the whole element, the whole member as one element. But actually, you can break this element into 2 members. You can also do it this way, if you like. You can cut one member into a set of truss members. Depends on how you do the cutting. The cutting is not, it's quite general. There are many cutting methods. You are not necessary to change into one member. You can change to 2 or 3 truss member. Depends on how you want to model the structures. If you cut the whole structures into more elements, then you can get a more accurate result. You can get more information But the consequence is that the problem size become bigger. In terms of mathematics, which means that the matrix become bigger. Then you need to solve bigger matrix problems. For wall, you can't count it as a truss member, right? For wall, you have to use every element, as I spoken at the beginning. Wall. For wall, we have nodes as well. One element, 4 nodes, and the second element, also 4 nodes. Some are common, some are isolated, right? This concept is called discretizations. Discretizations. We cut a continuous structures. At the beginning, a truss member, a wall, is a continuous member. They're continuous. But after cutting, we can describe their properties at isolated nodes. Same for wall. You can describe the force and displacement at the nodes. That's why we call that discretizations. Change a continuous problem to a discrete problem so that you can solve it mathematically instead of solving differential equation. You can use a matrix approach right here to solve the problems. What I mean is that if you treat the problem as a continuous member, then that means you have to solve differential equations mathematically. But here, if you discretize the structures, it becomes a matrix equations, not differential equations. It makes the problem more easy to solve. At the beginning, we would like to introduce some terminology, help you to understand the meaning. As mentioned right here, each member has 2 nodes. Generally, each member has 2 nodes, 2 ends, one on the left, one on the right. We call it nodes, which mean end of member. One member, generally, we have 2 nodes. And each node, we have nodal displacement. Nodal means a node. The displacement at the nodes, we call that nodal displacement. One member, 2 nodes. Each node we have some possible displacement. The displacement, we call this degrees of freedom. Degrees of freedom. Degrees of freedoms are the possible movements at the member ends. For a truss member, you can see that a truss member, the blue line is undeformed positions, okay? After the application of loading, the truss member may move vertically and horizontally. In terms of the picture right here, you can see that when a structure deforms, you can describe the deformation by 2 nodes. The left-hand side one and the right-hand side one. The left-hand side node is under vertical movement and horizontal movement to the right. The right-hand side node is under vertical movement and horizontal movement to the left. You can describe the deformation of a member by their node properties. It's quite clear in this picture. So you can see that each node, we have 2 possible movements. Say, for example, here, this node may probably under horizontal and vertical movements. Same for the other nodes on the left-hand side. These possible movements are called degrees of freedom, DOF in short. This is a general terms we keep using in this chapter, degrees of freedom. Degrees of freedom means the possible movements. Now remember this term, possible movements. Some movements can be 0. Some movements can be 0, as you will see very soon. Well, we understand the number of degrees of freedom. For one member, one truss member, we have totally 4 possible movements, 2 on the right, 2 on the left. To make our communication more easy, normally we give them some number. So for example, I use number 1 for the horizontal movement on the right, number 2 for the vertical movement on the right as well. We give them some number so that we can communicate in a consistent manner, right? Rather than saying left, right, up, down, here, I can directly mention, oh, displacement 1, displacement 2, and so on. Then you can see where they are, right? This is the meaning of the code number. Help you to identify the position easily. Similarly, the arrangement of code number is totally arbitrary. You can assign code number in any order. It will not affect the calculations. I mean, it will not affect the results. You can always get the same results, no matter what code number you are using. They just help you to communicate. But in the textbook, they have some suggestions to guide you to set up the code number. It may help you to formulate the problem easily a little bit. And the other things is called constrained degrees of freedom, unconstrained degrees of freedom. As we've spoken in the second point, now you know how to define degrees of freedom. Degrees of freedom means the possible movements at different nodes. But you can see that for trust structures, we have boundary conditions, we have support conditions we go through at the beginning, right? Support prevents some movements, right? That's why some movements are equal to 0. Say, for example, for this simply support the beams, simply support the truss, we are talking about truss right here. One end is pin, one end is a roller support. From this picture, you need to know how to identify which displacement are 0, which are non-zero. Now, that's why I mentioned in the introduction sections, you have to understand the support condition clearly. For this one, pin support prevent all possible movements. Pin support prevent all translational movements. They cannot move horizontally. They cannot move vertically at this point. If the movement is restricted by the support, then we give them a term called constrained degrees of freedom. Constrained degrees of freedom means displacement is prevented by, the movement is prevented by the support, constrained by the support, and the value equal to 0 right here. For roller support, roller support allow horizontal movement. So the horizontal movement is unknown, free to move. It can be moving to the right, moving to the left, depends on the loading. This freedom, we call that unconstrained degrees of freedom. Direction which is free to move. That's why we have these two terms, constrained and unconstrained. My opinion is that the terms are actually, I think, is not very important. More important is you need to know how to identify which positions you have no displacement, which position is free to move. I think these two statements is more important. The term is not very important, but the meaning is important. You have to know how to identify the position where you have no displacement, where you have unknown displacement. Okay. When you solve our structural problems, you need to find out the value of this question mark, or displacement of a member. Here is 0, right? No vertical movement at the roller support. This is the terminology you have to know. Degrees of freedom, code number, and then we have two terms, constrained, unconstrained degrees of freedom. They mean some displacement are 0, some are free to move. There is also one term called degree of kinematic indeterminacy. Degree of kinematic indeterminacy. This term simply means the number of unknown displacement. Degree of indeterminacy means the number of unknown displacement, the unknown that we have to solve mathematically. Using the same problems are truss structures, the same truss element, one end pin, one end roller. As we mentioned before, we have two nodes. Node on the left, node on the right. For each node, we have 2 degrees of freedom for each node, one horizontal, one vertical. And then you have to assign code number. You have to assign code number to describe the movements. And as I mentioned right here, you can assign code number in arbitrary manner. In theory, you can assign code number in arbitrary manner. But if you want to follow the textbook suggestions, the textbook suggests you to assign lowest code number starting from the position with unknown displacement first. This is the suggestions by the textbook. Try to assign code number starting from the position with unknown displacement. So according to our previous discussion, for this simply supported member, the horizontal direction on the right is unknown displacement. So according to this picture, we assign number 1 at this arrow. The code is unknown. I try to follow the textbook method first. Later on, I will show you what happens if you does not follow the textbook suggestions. You can always solve the problems, but you have to change the the matrix may look a little bit different. You have to rearrange the element to get those important informations. But anyway, at the beginning, we try to follow the textbook methods. One is used to assign at unknown displacement. The remaining 3 are known displacement, right? Constrained displacement, they're all 0. And how to assign the remaining 3 positions? You can assign arbitrarily. Since we assign number 1 at the right-hand side node, so I think in this case, we can assign from the right to the left, right? 1, 2, and then 3, 4. We can arrange in this manner, just arbitrarily. We have 1 unknown displacement, and 1 unconstrained degrees of freedom, and degrees of freedom 1. Degrees of freedom 2, 3, 4 are 0 displacement, or you may call this constrained degrees of freedom. They are 0 in this problem. Then what about the degrees of kinematic indeterminacy? Degree of indeterminacy means number of unknown displacement. So in this problem, the degree of kinematic indeterminacy is equal to 1 in this problem. Although this is just some introduction of simplest method, but this concept is highly important. This concept is highly important. You have to firstly identify the support conditions and also the position of unknown displacement. Otherwise, when you apply simplest method, you cannot solve the problems if you cannot identify where you have unknown displacements, or you will get the wrong result. So please make sure that you know how to identify what is so-called unconstrained and constrained degrees of freedom, their positions. They will totally affect you how to formulate the problems, how to solve the problems. Some of our pictures. In our first chapter, we will firstly go through trust element. Trust is an actually loaded member. We have axial force, we have deformations. And then the second topic, maybe next week, we will discuss beam. Beam is also very common structural elements. Beam used to handle shear and bending. When you want to draw shear force and moment diagram, then you have to use beam element to analyze structures and then solve it. The last part, topic 3. Topic 3, frame element. Frame element is the most general element used to capture all the things, axial, shear, and bending. But it is not new because you can simply add up truss beam, then it becomes frame. The formulations. Truss used to handle axial behavior. Beam used to handle shear and bending behavior. So frame here, just add them up together. Then you can handle both axial, shear, and bending. Okay. In the notes, I use Q to denote force. I use D to denote displacements. Different textbooks may have different symbol. Some may use F for force, but in my notes here, I use Q. Displacement, I use D. I remember that some textbook may use U or X for displacement, but they're just symbol. Okay, the second part, truss. Remember this matrix, truss. In this part, we go to trust element to see how we can formulate the problems in member level, trust member. We try to consider the formulation for trust member. And then later on, you can apply this formula to all trust members. One structure is composed of many trust members, right? You can use this equation n times. And then later on, you can combine them together. Then it becomes a structural problems. At the beginning, let us have a look how you can formulate a problem. And this also explains why we can convert a structural problems into a matrix problems. In this part, we are going to establish the Stevens matrix for a single trust member in terms of their local x prime and y prime coordinates. When you derive equation, we have to firstly set up the coordinate system. Here we set up a so-called local coordinate system. Local. For local coordinate system, we normally use a dot on the top right-hand corner to mention that it is a local system. Local to the member. Local to the member. The dot here we call we call prime, x prime and y prime. They are the local coordinate system. Why we call this local? Because this is how we define the local coordinate system. X prime. X prime is the axis that along the member length. X prime is the axis that along the member length. Y prime is orthogonal to x prime. Okay. Why local? Because x prime depends on the orientation of member. If you have a horizontal member, then this becomes the local system. If you have a vertical member, then it becomes the local coordinate system. Okay, x prime is always along the member length. We call that local to the member. How to derive the Stevens matrix? How to derive the equation for a trust member? We would like to apply principle of superposition. We use superpositions. We break down the problems into two cases. Case one, we have one trust member here, right? One trust member, we have two nodes. One on the right, one on the left. As mentioned in the previous part, we have some possible movements at two nodes. To use superpositions, we would like to break this problem into two scenarios. Scenario one. For scenario one, we just consider displacement and near end node. What is near end node? Near end node means the node at near the origin of the local coordinate system. Near end node, n means near to the origin of our coordinate system. N, near end node. The opposite one is far end node, f. We have node n and node f. N represents the node coincide with the local system. F is the other one, far from the origin. Okay, near n and far n. Go back to here. Case one. Case one, we just consider displacement at near end node, and the value is equal to dn. The subscript n stands for the position, not n. D stands for displacement. Okay, dn. We consider positive displacement at near end node. The other n, far n, held pinned. That means no displacement at far end node. This is case one. We only consider displacement on one side and then ignore the other side. Then you can understand what is case two immediately, right? Case two, the opposite. And then when you add up the two scenarios together, it becomes a general situation. This is how you use superposition. We will discuss in the next few pages. But firstly, let us consider case one. Now we have some explanation about NF. this is the orientations. Orientation of the member. The member is oriented from node N to node F. Member orientation is also important to identify the direction of members. Orientation points to node F, pointed to node F from the other one N. Now we consider Dn at node N. Then what about the forces? If node N is under displacement Dn, what about the internal forces along the member? Truss is an actually loaded member. Well, to make things general, I assume that we have two forces. One is Q prime N, which is the force applied at node N. Over here, you can see that we try to describe the force in displacement at the node only. We try to describe force in displacement at the node only. I ignore the middle part, okay? We just describe the quantity at the node N, node F. We totally ignore what happened at the middle. Node N is possibly under force. The force can be tension, can be compression, depends on the movement. Right? To make things general, to make the equation more general, I assume that the forces are pointing along x prime. I assume that the forces at node N and node F are pointing along x prime directions. Okay? When you do the calculation, if you find that the value is negative, negative means the force should be opposite. Okay? This is how we derive the equation. Assume that the member, the numbers, pointing along the positive directions. During your calculations, if you find that the value is negative, then you can reverse the direction yourself. That's why we assume that Qn, Qf, they are pointing along x prime in the picture. Now the meaning right here, Q means force, the prime means local, with respect to the local coordinate system. N stands for the node, right? Node. We have Q prime N and Q prime F. How to find out the values? You can recall this famous equation, Hooke's law. Hooke's law helps us to solve many problems. Hooke's law, stress equal to Young modulus times the strength. What is stress? Stress is equal to force over area. What is strain? Strain is equal to deformation over the length of member. Then you can rearrange this equation a little bit. Force Q equal to EA over L times D, right? Force equal to EA over L times D. From this equation, you can see the stiffness term easily. The stiffness of truss member is equal to EA over L. It makes sense. Stiffness is proportional to the elastic property E, the cross-sectional area A, inversely proportional to the length of member. It quite makes sense, right? This is the stiffness of a member. The bigger the structure is, the higher the stiffness, or the longer the member, the lower the stiffness. Right? It quite makes sense. You can use this equation to find out the relationship at node N and node F separately. At node N, we apply this Hooke's law separately at the two nodes, node N and node F. At node N, the force Q prime N is equal to EA over L times Dn, right? At node N, the displacement is equal to Dn. The corresponding force is equal to Q prime N. They are correlated using this force displacement relationship. Use the same equation again at the other node. You get similar equation, but Firstly, you can see that the displacement due to dn, right? Because we are talking about case one. Case one, we just consider dn, no df, okay? And second, you can see a negative sign at the beginning. Why? When you take a look of the picture right here on the right-hand side, now you will undergo positive movement, which means that the member is under shortening. The member is under shortening. For a member under shortening, we expect that the member should be in compression. For a member in compression, the force on the left is pointing this direction, right? The force on the right is pointing to the opposite direction. This is what we understand from compressions. Opposite to our initial definitions. That's why we put minus signs in the equation for Q prime F. Change the direction. This is how you can find out the force displacement relationship for case one. Case one, under only positive displacement at the end. Then you can move on to the other scenario, case two. Case two is just opposite. We assume that there is no displacement at node N. We have positive displacement at node F. Case two. The member is now under displacement at node F, but nothing at node N. Then you can do the same thing. Construct the force displacement equation again at the two nodes. Here I use 2 double prime to denote that it is second case, case two. Okay, the force at node N right here is equal to minus EA over L times dF. Scenario two, we just consider dF but no dN, which means that the member is under elongation. Member under elongation. For a member under elongation, which means it is in tension. For a member in tension, the force on the left-hand side is opposite to our definition in the pictures. So there's a minus sign. Q double prime F positive equal to EA over L times dF. So now we have the displacement equation for case one and case two. They are not completed. You have to combine the two scenarios together using principle of superpositions. Because in reality, both ends is under forces. Right, dN, dF. Oh, I think this should be subscript F. In reality, a truss element can be under both dN and dF, as shown in the pictures. They appear together, right? Not individually, appear together simultaneously. In this case, what is the force displacement relationship? You don't need to recalculate again because you can superimpose the previous two scenarios together. Node N. Node N, the force at node N is now due to combined effect of dN and dF. From case one, you can find out the expression due to dN. From case two, you can find out the expression due to dF. Now you can superimpose them together, add them up together. Then it becomes the equation of Qn due to dN and dF. Similarly, you can use the same concept at node F. This becomes our final equations. Node N, the force at node N, Qn, is equal to the effect due to dN and the effect due to dF. The force at node F, similarly, is equal to the combined effect of dN and dF. We have two equations for the two nodes. If you see this equation, they are arranged in similar manner, you can convert them into a matrix form. Okay, you can convert them into a matrix form. To make the equation more compact and more simple, you can always convert them back to separate equations. If you're familiar with matrix algebra, the first row, a matrix equation, which actually means a set of equations. The first row, the first equation, can be reconstructed by using matrix multiplications. This row times this column vector give you back the first equation, right? You can use matrix multiplication, convert them back to individual equations. Don't be scared by matrix. Matrix actually means a collection of a set of equations. By doing so, you can apply those matrix algebra concepts to solve the problems, make the calculation more easy, to use the concept of matrix operations. The left-hand side is the force vector at the two ends. The right-hand side is the displacement vector at the two ends. The middle, stiffness matrix. From this equation, you can see why we have matrix, because we firstly discretize the structures into two nodes. We describe the force displacement using two discrete nodes. And then we try to formulate the force displacement equation here for each node, put them together. It becomes this matrix equation. We derive this equation with respect to the local coordinate system. So once you know the local coordinate system, you can use this equation to find out maybe the force or displacement of any truss member. Here just mentioned discretizations. Discrete a continuous truss member into two nodes member. What happened at the middle? We are not really sure because there's no node at the middles. We only know the quantity at the positions with nodes by solving the equations. You can move the constant EA over L outside the matrix, become this one in matrix form. You can see EA over L inside the matrix. So to make the things more easy, you can extract these common terms out, become these equations. Sometimes we don't want to write down the matrix too many times, too many symbols. So normally we use a bolded letter to denote vectors or matrices. This bolded letter Q denote force vector. This bolded D means displacement vector. Bolded K prime means the local stiffness matrix. We use this bolded equation to denote the matrix equation. K prime is so-called the member stiffness matrices in local coordinate system. Two important terms. Firstly, member. This is the member matrix, not the whole structures. A whole structure is composed of more than one members, right? We have to combine member stiffness matrix later. So that becomes a matrix for whole structures. Second, local coordinate. This matrix is derived with respect to the local coordinate system. Different members may have different orientation, so they have different directions. The element inside the stiffness matrix, K, the element inside the stiffness matrix, if you like, you can call this member stiffness influence coefficients. It's just the name of the element inside the matrix. It's called stiffness influence coefficients. Symbolically, it is equal to Kij. Ij are the row index and column index. Say, for example, this is K11, K12, and so on. Sometimes we don't want to write the things too many times, so we can use this kind of index location, Kij, for I equal to 1 to 2, for j equal to 1 to 2, and so on. If we have a large scale matrix, you can also use this notation, right? Ij for I equal to 1 to something, j equal to 1 to something, right? To make the things more general, rather than writing down this thing too many times. this is the physical meaning of stiffness influence coefficients, Kij, K prime Ij. K prime Ij is divided at the force at the joint I when the structure is under a unit displacement applied at node J, at joint J. K is the element inside the stiffness matrix. It is divided at force at one position due to unit displacement. Unit displacement, unit mean 1. Unit mean 1. Actually, the stiffness matrix represents the force due to unit displacement. What does it mean? When we derive the equation right here, you can see that if you change the displacement to 1, then you can see the force become the stiffness terms, right? The stiffness actually means force per length, per unit length. So you can use this to explain what is the meaning of the element inside the stiffness matrix. The element inside the stiffness matrix is also related to forces under unit displacement. Same things. If you understand this concept, you can also use this concept to derive the stiffness matrix. Same things. Symbolic notation, K11, K12, K21, K22. Some textbooks like to use this index notation, Kij. Then you can find out what is, say for example, in this picture, we under only unit displacement at node N, equivalent to our case 1 at the beginning. Then you can find out we have two actual forces, one at the node F, the other one at node F. They are equivalent to K11 and K21. The first column, actually the first column inside the stiffness matrix is the force due to unit displacement at node N. Then what about the second column? The force due to unit displacement at node F. You can apply unit displacement separately on the structures and then find out the reactions. The reaction represents the stiffness element inside the matrix. You can also do this approach to derive the matrices. Okay, just show you more background, not just on derivations. In this module, I mainly focus on assessing you how to use the equation. Okay, how to solve the problems. Derivations is not is basically for your information. I will not directly ask you to derive things. Okay, but I think it's good to know more about stiffness matrix, not just using it. It's good to know the background. And also some remarks. The remarks. Stiffness matrix, when you add up all the elements along a single row, single column, it will be equal to 0, basically because of equilibriums. The stiffness matrix, this is important. The stiffness matrix is symmetrical. It's symmetrical. Okay, remember this property. The matrix should be symmetrical. Otherwise, that means you do something wrong in your calculation. If you find that the matrix is not symmetrical. What is symmetric matrix? Given a matrix, we have a diagonal line right here. Symmetric matrix means you can flip one corner to the other side to reproduce the whole matrix, which means symmetrical. Okay, you can flip one side to the other side to construct the whole matrix, which means symmetrical. Stiffness matrix should be symmetrical. Otherwise, which means you do something wrong in your calculations. This also helps you to simplify your calculation, right? Because that means you just need to know one part of it, not the whole things. If you know the top corner, then you can reproduce the bottom corner immediately. Right? You just need to know one half. And the last point is that to solve problems, you need to impose some boundary conditions. We will discuss this later. Boundary conditions mean the support conditions. When you just take a look of this equation, you can't solve it. You can't solve it. You have to put some boundary conditions or apply loading Otherwise, you can't solve the problems. The last statement just showed you one term, finite element method. Maybe you have seen this term before. Siebert's method is quite similar to finite element method. We discretize members into different relative finite elements and then put them together. We derive our equation, we derive our matrix using equilibrium before, right, for displacement relationships. But when you do a research, you can see that actually you can derive our formula, our matrix, using the other approach. You can derive our Siebert's matrix using energy principle, like virtual work principle. We have more than one way to derive the formula. That is how we get so-called finite element equations. If you like, you may do a research for this topic, FEM. Okay, I just want to tell you this term, FEM, finite element method. The outcome is also something like Siebert's matrix, something like this. But they start from the other principles to work out the expressions. One simple illustrative example, how we use the equations. This one is very, very simple, just let you know how to use the equations. Normally, our question is slightly more complicated, not as simple as this one. So given a single truss member under elongation, the elongation is 10 units. Then what we can get when you use our full displacement relationship, Q equal to K prime D. Assume that we have node 1 on the left and node 2 on the right. Then we have one force, Q1, we have the other force, Q2, at node 2. And then we have also D1 and D2, if you like. D1, D2. We describe our force and displacement at the node. We have node 1 and node 2 in the pictures. So in general, for a truss member, we can put down this force displacement equation immediately, symbolically, Q1, Q2, D1, D2. And then you can put down the well-defined conditions into the equations. From this picture, what we get? D1. D1 is the displacement at the fixed end. So it is equal to 0. D2. D2 I give you directly in the picture. That's why I call this oversimple. D2, 10. Substitute this well-defined equation, well-defined property in these equations. Then you can see that you can use this equation to find out forces Q1, Q2. Okay, Q1 and Q2 can be obtained immediately. It depends on what information you have. If you know the force, then you can use it to find out displacement. If you know the displacement, then you can use it to find out the forces. Okay, just illustration show you how to use the equation. As spoken before, you can't use the equation directly. You need to provide some conditions, boundary conditions. Otherwise, you can't solve the problems. Right? When you just take a look on this problem, you cannot get anything. You have to input some support condition or the loading. Otherwise, you can't solve it. Mathematically, you can understand mathematically, right? You have two equations. 4 unknowns, can't solve, right? 2 equations can only handle 2 unknowns. Right here, we have 2 unknowns. Then you can find out the unique solutions mathematically. So what we have, in this part, we actually go through something about the background of Siebert's method. Siebert's method is a discretization approach, converts a continuous structure to well-defined discrete element. And then we also discuss how to derive the equation for truss element. This topic mainly focuses on truss. In the future, you will learn how to derive beam element and frame element. And then we discuss some terminologies, something that you have to know. So for example, degrees of freedom, code number, kinematic indeterminacy. What we have also node, right? Node and members, near end node, far end node, local coordinate systems. We have many terms covered in this part, right? So try to review what we have discussed when you have time. And then we have discussed some how to derive our member sequence matrix for trust element. And then I show you one very simple example to see how to use it. But what next? Next, before starting the next part, maybe we can take a short break. We can take another 5 minutes break.